Let's recap. In the first video, we computed the Maclaurin series for the sine function and found that it was equal to x minus x cubed over 3 factorial plus x to the fifth over 5 factorial, etc. In the second video, we derived the differential equation describing the motion of a simple pendulum. To pull this off, we use the small angle approximation for the sine function. This comes from the Maclaurin series and the fact that the higher order terms have a very small contribution to the overall value as long as x is very small. When we were finished, we saw that this differential equation matched that of a simple harmonic oscillator, proving that their behaviors are the same. Now, we're going to study the motion of tall buildings, and in order to do this, I'm going to draw a diagram. I'm going to need two walls and a roof. I need the building to be standing on something, and it's probably got some windows, definitely some engineers, and the engineers have some kind of sensors or something hooked up to the very top center of the building. This is the midline of the building, and we're going to say that this building is currently at equilibrium. Equilibrium means a couple of things. 1. The displacement, x, is 0. 2. If we say that capital U is the potential energy of the building as a function of x, U is an unknown function and it's probably very complicated, but we can say that when x equals 0, the potential energy is at a minimum. This building doesn't want to move around. It doesn't want to wiggle. Now, for some math. We know that u of x has a Maclaurin series expansion, and here it is. A is equal to 0. I've abbreviated du dx evaluated as 0 as u prime of 0, etc. I really need to simplify this. I know that u of 0, or u naught, is the minimum potential energy. This means I can get away with assigning u naught is equal to 0. This is very common practice. Next, I know that 0 is a local min for u. This means that u prime of 0 must be equal to 0. U may not look pretty, but if 0 is a local min, the slope of the tangent line must be 0. Finally, regarding the third derivative of u and above, for small x, we know that the higher order terms of the series make extremely small contributions to the value of capital U. So we can cross them off even if they're not exactly 0. So we have u of 0 equals 0, u prime of 0 equals 0. We're ignoring these terms, order 3 and above, and we're left with the quadratic term only. And since u prime prime of 0 is a constant, I feel like renaming it k. Why not? Here's what we've got. U of x equals 1/2 kx squared. Near the origin, the potential energy function looks like a parabola. We know that the force function associated to this potential energy function is F equals negative du dx, but this implies that F is equal to negative kx. The force is proportional to the displacement, and this is exactly how simple harmonic motion works. If the potential energy function is quadratic, this is what we have, then the force function is proportional to the displacement. This is exactly simple harmonic motion. Buildings move like simple harmonic oscillators.